In this video, we are going to calculate the normal contact force on a ball moving along a semicircular track when the ball is moving at the bottom point of the track. The center of the semicircular track is the point O, and the radius capital R of the track is equal to 0.800 meter. Let the mass m of the ball be 4.0 kilogram. The ball is released from rest at the highest point on the track, and we are going to call this point of release the point A. The speed of the ball at this point is VA, which is simply 0 because we release it at rest, and therefore this means that the kinetic energy of the ball at this point is also 0. So we can write EKA equals to 0. The ball then moves along the circle from point A to the bottom point of the track, which we call the point B. The speed of the ball at point B, we are going to call it VB. So the kinetic energy of the ball at this point is EKB, which can be written in terms of the speed at point B as EKB equals to half mVB squared. The increase in kinetic energy of the ball when it moves from point A to point B is delta EK AB equals to EKB minus EKA, which is simply final kinetic energy minus initial kinetic energy. This can be written in terms of the speed as half mVB squared minus half mVA squared. And we know that VA is 0, so we obtain half mVB squared finally. This increase in kinetic energy comes from the loss in the gravitational potential energy of the Earth ball system when the ball moves from point A to point B. To calculate the loss in gravitational potential energy, we need to remember that the formula for the increase in gravitational potential energy is given by delta EP equals to mg delta H, where delta EP is the increase in gravitational potential energy, m is the mass of the ball, and delta H is the increase in vertical height. When moving from point A to point B, the ball falls by a vertical height equals to capital R, which is simply the radius of the track. Now remember this: a decrease in vertical height of R is equal to an increase in vertical height of minus R. Therefore, we can write delta H equals to minus R. Hence, we obtain delta EP AB, the AB simply means from A to B, equals to minus mg capital R. The minus is simply telling us that this is a decrease in gravitational potential energy, which can be written as EPAB loss equals to mg capital R. Then we can equate delta EKAB equals to delta EPAB loss, which is simply the conservation of energy in the absence of resistive forces. And therefore, we obtain half mVB squared equals to mgr. Now let me clarify something. Here we have said delta EKAB which is simply the increase in kinetic energy when the ball moves from point A to point B, is equal to the delta EP AB loss, which is simply the decrease in gravitational potential energy of the earth ball system when the ball moves from point A to point B. Another way of writing this is to say delta EK AB, which is the increase in kinetic energy from point A to point B, plus delta EP AB, which is the increase in gravitational potential energy from point A to point B, is equal to 0. If we substitute delta EK AB as half m VB squared, and we substitute delta EP AB as minus mgr equals to 0, we can rearrange it and obtain half mvb squared equals to mgr, which is exactly what we obtained previously when we were working in terms of the loss in gravitational potential energy equals to the gain in kinetic energy. In the second way of formulating the problem, we worked only in terms of gain. The net gain is 0. This is in accordance with the law of conservation of energy in the absence of resistive forces. Hence, finally, we obtain Vb equals to square root of 2gr. If we substitute r is equal to 0.800 meter and g equals to 9.81 Newton per kilogram, we obtain Vb equals to 3.96 meter per second to 3 significant figures. Now, to find the normal contact force at the point B, all we must remember is that for a body to move along the arc of a circle, a component of the resultant force must act on the body towards the center of the circle. This component of the resultant force is what we call as the centripetal force, and it is related to the speed as follows. So we are going to write the centripetal force F capital R C equals to mvb squared divided by R. Now the reason why I put a subscript capital R next to the F is simply to tell you that this is a resultant force. So when the ball is at the bottom of the track, it will require a component of the resultant force acting on it vertically upwards, because the center of the semicircle is vertically above the point B. So, right now, we know that the component of the resultant force along the vertical is FRC, and that it points vertically upwards. Therefore, all forces acting on the ball at the point B must give a resultant force that has a component vertically upwards towards the point O and has a magnitude mvb squared divided by R. The two forces acting on the ball are the weight W and the normal contact force Fn. As you can see, I have placed an arrow on top of each symbol W and Fn to tell you that these two quantities are vector quantities. So we can write the resultant force on the ball as follows: Fr equals to W plus Fn. And as you can see, I've maintained the vector notation. I kept the arrow above the symbols to tell you that this addition is a vector addition, and therefore directions has to be taken into account when performing this addition. The direction of the weight W is vertically downwards. This we know right from the start because the force of gravity is vertically downwards. The direction of Fr is vertically upwards because Fr has to provide the centripetal force. And the centripetal force has to point vertically upwards because the center of the semicircle is vertically above the point B. However, we don't know the direction of the normal contact force Fn. But remember that the normal contact force is always perpendicular to the surface at the point of contact. At the point B, the track is horizontal. Therefore, the normal contact force must be along the vertical in order for it to be perpendicular to the surface at the point B. Hence, this allows us to conclude that the three forces Fr, W, Fn are parallel to each other, except that I don't know the direction of the normal contact force. I know it is along the vertical, but I don't know whether it points upwards or downwards. Therefore, our vector equation simply consists of parallel vectors. So we are simply adding parallel vectors here. When adding parallel vectors, all we need to do is to place an axis. Here, I'm going to place my y-axis pointing vertically downwards. Once I have my y-axis in place, the vector equation can be written like this. Fry equals to Wy plus Fny, where Fry is the component of the resultant force in the direction of the y-axis. Wy is the component of the weight in the direction of the y-axis. Fny is the component of the normal contact force in the direction of the y-axis. I can substitute Fry as minus Frc, which is equal to minus mvb squared over r. The minus here is because the centripetal force is contributing its value opposite to my y-axis. So I substitute it as a negative, which can be read as the resultant force is contributing minus mvb square r in the direction of my y-axis. Pay attention to what I have said. My y-axis is vertically downwards. The centripetal force have already been deduced to be pointing vertically upwards. So it is contributing its value vertically upwards and therefore opposite to my y-axis. So we are going to say that it is contributing minus mvb square over r in the direction of my y-axis. For the weight, which is vertically downwards, we substitute Wy equals to mg, positive. Why? Because the weight is contributing its value in the direction of my y-axis. After substituting, I should get the equation like this. Minus mvb squared over r equals to mg plus f and y. So I rearrange to make f and y subject our formula, and then I just substitute m, r, vb and g, and I should obtain f and y equals to minus 118 Newton to 3 significant figures. Now, why do we have a minus here? In fact, the minus is consistent with our y-axis. What my answer is telling me is my normal contact force is contributing a value of minus 118 Newton in the direction of my y-axis. Therefore, it means that the normal contact force is contributing 118 Newton in the opposite direction to my y-axis. In simpler words, we can simply say that it is contributing 118 Newton vertically upwards. So this is how you manipulate vectors consistently by respecting their directions. So if you like the video, don't forget to click the like button, subscribe on the channel, and share the video. Thank you very much. Until next time.